Okay, hello everyone. This is just what we have done last Friday, because on Friday I didn't have much equipment to record the session. So I would like just to give you some quick review and recap what we have done so far on the Friday class. So we are in the chapter 11. We now move to what we call the Taylor and Maclaurin series. So before, we have learned that the power series can be represented as a function, right? Now, this Taylor and Maclaurin is actually how we can define or describe the power series as a function in general procedure or general rules. Okay, so let's start with the what's the definition. So suppose that we have, for example, we now have the idea on, let me write here, 1 over 1 minus x. That is actually the definition for our original power series, right? Okay, and we can rewrite the power series in general with that formula. Okay, so we have a coefficient c, and also the x minus a. A stands for the center of the interval of convergences. So x minus a and x plus a, that's becoming the radius of the convergences. Okay. Okay, and we can express this power series, okay, by taking the function and then taking some n. Okay, let's start from n equals 0, which giving you c0, and then plus we start to take n equal 1, so we have c1 and then x minus a and then 1, right? I didn't need to word that. And then c2, x minus a squared, right? And then plus c3 and then plus c4, and then maybe plus the last one, the c5, and plus dot. Okay, and the ratio should be less than the r. Okay, so if you put the x equal a, so f of a, if you plug in a to substitute x, then we only have the constant. Okay, and then from this function we could try to take derivative, and then we are going to derive all the components. Okay, c0 becomes 0, c1 become c1 like that, and then 2 c2 x minus a plus 3 c3 x minus a squared, right? And then 4 c4 x minus a cubed plus 5 c5 x minus a with power of 4. Okay, and then the same, the ratio. Okay, we need to state the convergences, and then another derivative we can take. Oh, maybe before this, let me write the f prime a is equal c1, and then derive again the second derivative now. So this will be 2c2 plus 3. Let me write, because it should be 2 going to be here, right? So it should be 6, right? So but I would like to write in terms of 3 multiplied by 2. Okay, so let's doing that. and then 4 multiplied by 3, and then C4, and then plus, okay, 5, okay, and then plus dot dot dot, same, x minus a less r, and we could also plug in x equal a inside these equations, which give you the 2c2, okay, and then let's take another one, okay, so this will be 3 multiplied by 2, c3, okay, and then plus, now it's become 4 multiplied by 3 multiplied by 2, okay, and then 5 multiplied by 4 multiplied by 3, and then this will be 3 multiplied by 2, c3. Okay, let's try one more, last one. So the fourth derivative, so this will be 0, so 4 by 3 by 2, c4, and then plus 5, 4, 3, 2, and then c5, and then plus dot dot dot. And we could see that this fourth derivative, when we plug in a, this will be 4 multiplied by 3 by 2, c4. Now notice that we've made something interesting here, right? So we have 2, 3, 2, 4, 3, 2, which equal to, this is 2 factorial, 3 factorial, 4 factorial, and even we can think that this first one is just 1 factorial. So this pattern we can write in more general. So we have f with some n for the how many times we derive the n derivative. So this could be 2 multiplied by 3 multiplied by 4 by 5 by dot dot dot, it's up until n, and then cn, or we could say that this will be n factorial of n multiplied with cn. And this is the pattern that we have generalized, okay, and then we can rewrite in terms of c that this is going to be this forms, okay. Now this form we could exchange cn, okay, so we could write the more generalized formula, okay, that we have here, okay. So if f is a power series representation at a, that is if, okay, these functions can be described in power series, we have some certain radius value to be converged, and then the coefficients are given by this formula, okay. And then let's substitute back this formula, this cn, go to this cn, okay. So if we put back into that cn, then we get this, okay, which we have, I think, done in previous parts, which is having 1 factorial, 2 factorial, 3 factorial, and so on and so forth. So this is C0, this is C1, C2, C3, and so forth and so on. This is what we call the Taylor series. Okay. And then if A is 0, then we could also write a new perspective or a new series, which we call the Maclaurin series. So actually they are both the same. The difference is just the Maclaurin series is when A is equal to 0. Okay. So why the Maclaurin series become important? Because many cases they are frequently comes up in especially in engineering or in calculus, then we define that as a new series which we call the Maclaurin of okay, now we could start taking some special functions in Maclaurin series, and then how we could develop or set up the arrangement. For example, we could start from the one that we have done before. Okay, of course we know how to represent this in the power series. Okay, this is just this, right? And then we can express. Okay, we can express like that. But we can also try to arrange these functions as a Taylor series, okay, or as a Maclaurin series. So if we start from the f of x is 1 over 1 minus x, we set up when x equals 0. So this is 1. And then we take the derivative. So we derive this. So I hope you can derive this easily. I will just write the final result. And then plug in. And then another one. Is multiplied by 2, right? So this will be 2. And then the third one. So this will be 3, 2, 1. This will be 3, 2, 1, okay, or 6. Okay. So we could see that the f derivative, okay, this is 1 factorial, 1 factorial, 2 factorial, 3 factorial, and then you will see that the next derivative will be 4 factorial, 5 factorial, and so on and so forth. So we could write this as an n factorial divided by 1 minus x. Okay, 1 minus x, and then see that when the first derivative, it has 2 in the bottom. When the second derivative has 3, so we have additional 1 for each n derivatives. So we could take this as n plus 1 like that. Okay. So taking the x equals 0 to make it our Maclaurin series, we are going to have the n factorial. Okay, so what does this implies? So if we take the constant, the coefficient, the formula is this, right? And then we know that this power series has an n factorial for this f. Okay, so we can substitute, and then we see that it's just 1. Okay, it means that it is true. So we confirm that the function 1 over 1 minus x, if you write within the definition of the Maclaurin, this is equal to, okay, because this is equal 1, right? So this is what we call the this one is the Maclaurin setup, okay, or Maclaurin general formula. Okay, you can take notes for the Maclaurin. Okay, and we could also try to do the other example as well. Let's start simple, taking f of x equal e to the x. Okay, let's try to find a Maclaurin series. Okay, so as usual, we start by taking the f and then taking the x equals 0 for each one of the functions, and then the first derivative, e to the x, and you'll see that for the e, all the derivative terms will have the same e to the x, right? So we could just stop until this one, and we can make some conclusion that this is always equal to 1. So this means that we can write the terms. This is Maclaurin setup. Again, let me write so that you know and understand what this is. Okay. Now all the terms for the f will be 1. So this will be equal to, or let me write, so e to the x is, because the setup is just 1, so this will be x to the power of n, and then divide by n factorial. Okay. So this will be, we can expand this series. So we can start from n equals 0. So it will be 1, and then n equal 1. So we will have x over 1 factorial, and then x squared 2 factorial, like that, and so on and so forth. So you could see that we could expand this e to the x. But sometimes you still need to determine the convergences, like finding the radius or interval of convergences. We can apply the previous formula in the power series, which describe the how to find the ratio and so on. Right? We could start like to find r. We could take the ratio test. So we could take x and then multiply and then we can cancel this out. So we can have n factorial, or we can also cancel the n factorial with this, right? So we have oh, I forgot to cancel that. So we have this, right? Which is going to be 0 when we take the s. So as n going to be infinity, series will be 0. So all x will be converges. So r is everywhere. Okay. Okay, now okay, now the next question is, now we know that the e to the x, okay, let me write again this, the conclusion. This is equal to this, right? The question next is when or how we determine that e to the x has power series presentation. Okay. So of course this is going to be some proving. Okay. So if we take the original setup for the Taylor series, this will be f Okay, this will be converge, right? This will be converge, or this, let me write. The series will be converge if, or not if, this is converge, that we can say that the f of x is limit of sequence of the partial sums. So similar to what we have done in the previous sections, which we described the series can be described as a limit sequence of the partial sums. So what is partial sum? Partial sums is, so if we take let's say the e to the x, okay, we could take the this part here, right? So the partial sum is we take some part of it, like this one is S1, okay, so this is S0, so we take from S1, and then this will be S2, this will be S3. So why we need the partial sum? Because we are going to develop a new sequences that will end at some point, okay? Because if we just let the series going expanded, they are the series will going infinitely, right? So we don't know how to stop the series. So we need to take some steps and then stop the series at certain point. So we take approach for the partial sums. So in this case, we define as t as our partial sums, Tn of x. This will describe as the same but we may take differences here, not n but maybe I, and then we limit this up until n. Okay, so f will all become I, but basically they are the same setup with the original f, okay? But we are just taking this and make it some certain stop. Okay, so if we take this, we are going to have a series that will let me take this a little bit to the left, okay, and this will be dot 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 plus we are going to end up until this n, right? Okay, okay, now let's see. Okay, well, this is supposed to be the title, when a function represented as a Taylor series. Okay, so if the f of x is e to the x, and we know we can describe e to the x as this, right? Then we could describe the partial sum. In this case, is the t1, t2, and then t3. So imagine we have this t1, t2, t3, and of course we are going to have some x, or some t up until n, right? Tn, it will be 1 plus x squared plus dot 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 x to the power of n. So you can imagine that within this t, we could somehow take the sum and then make it bigger using the limit. Okay, so imagine this will be getting larger and larger, and then we could describe in terms of visuals. Here we can graph the functions. Of course, the e to the x we can easily graph, right? can easily graph the red color there. And all the other partials, we could see how it goes. Okay, so let's start from the T1. Okay, let's start from here. T1 is just a line like that, and then T2 is the green one here. I think notice the one on the right side here. Okay? We are going to see how the T3, let's see, over here, T3, the blue one. Of course, this will be getting the downside here because of the cubic root, the cubic, right, the cubes. And then you could imagine that if we increase T3 to T4, maybe T4 is around here, and then maybe like that. Okay, and then T5, it will be that one, and you will see that it is getting closer and closer here, right? It's getting closer, which means that when we take the n larger and larger, the whole curve becoming closer to the original function e to the x. Okay, so we could say that the function f is actually limit as we take n larger and larger for this Tn of x. Okay, and of course these two different value has some certain small differences, right? We call that differences as a reminder r, which are the differences between the f and t. Or we could say the f is actually addition between t and r. So the r is, we call this is the remainder. So to make our theorem correct, or if we want to confirm that, then need to show that limit as n getting larger of r, it is going to be equal to 0. So we take the limit of our Tn, which means we are going to deconstruct the t between, becomes f minus r. So if we can prove that the limit of this r is 0, then we can prove that the limit of the t is equal to the function of x. So this provides the theorem. So if we have the r, which is the differences between f and t, if we take the limit of r, if it is equal to 0, then the f will be equal to the sum of the Taylor series. So f is equal to the limit of the t. Okay. Now, how to start to show that the limit of the r is equal to 0? So we can start by taking this inequality. Okay. So what this means is basically we start taking this value m. Okay. So m can be any value, but we start just taking m. So m will be value that describe the f derivative of the function. Okay. And then we also describe this m within the interval. Okay, this interval. Okay. Within this radius d. Okay, we set some number d. Okay. And then the remainder need to be satisfied within this. This is actually you could say that this is the Taylor series, right? The Taylor series is f This is Taylor series, right? So we take the Taylor series and then rewrite them to make our remainders inequality. Okay. So first, we assume, let's say we take n equal 1. So start n equal 1. So we have f2, which means second derivative. Okay. And then assume that this one is less equal m. Okay. This is 4. We start from a, and then we add d. So the x will be in between a and a plus d. Okay. So taking the integral both sides. So taking integral this dt, and then taking integral for m. Okay. So let me continue on the right side. Okay, let's start from here, and then we start to describe this, and then taking from a to x, okay. So f, so we take derivative, we take the integrations, it's less equal, sorry, it's less equal. Okay. So f prime x is less f prime a plus m x minus a, like that. Okay. So the integrals from a to the x, f prime t dt is less equal okay, and then we could set up the f of x minus f of a. Okay, so let me explain this for a while. Okay, so the second derivative is the one that we assume at the beginning. So to get to the f, we need to integrate twice, right? So first is this, and we get this, and then integrate once more, we get the last part here. Okay, and then what else? We can describe this. Okay. Okay, it's nicely done. Okay. Okay, now we have these expressions. Remember that for n equal 1, the R1 will be f of x minus T1, right? Which means that T1 can be described in terms of f. This will be f of a minus f prime a x minus a. Okay, which is this is actually the R1. Okay, so the R1 is less than or equal to m over 2x minus a squared. And if you take the same argument, for negative m, we get the same results and the same argument as well. Okay, so we take as a conclusion that the absolute value of R1, this will less equal m over 2 x minus a, or let me write squared. Okay, so if you want to prove this E, so prove e to the x is equal to sum of Maclaurin series. So to prove this, we start taking the function as e, and then take this expression. We need to make this for all n. Okay, and we take the ratio less equal d. D is any number, okay, any positive number. So the expression can be written as, which is always less equal to e to the power of d. Okay, so we can use the Taylor's inequality. So this is called the Taylor's inequality, but now we are going to make it into Maclaurin series, which we are going to input x or a equals 0. Okay, a equals 0. So we could take this. I think this will be later. Okay. So let's focus here first. So we take so a is 0 and m is e. Okay, now we can write the remainder. Okay, this is for the ratio less equal d. And this e to the d or the m, it's always the same for every for every part, right? For every part they are always the same. Okay, so we can say we can take the limit we can factor the e, and this will be equal what? So remember that this part here, this makes 0, or we can also take, so by squeeze theorem, the limit becomes 0. So we say that the limit of the r is 0, and then follows that the e to the x can be proved as x power n and n factorial. Okay. So this is proof how to prove that. The interesting on this E, okay, if we put if x equal 1, then E becomes, we can rewrite like this. So we can express E in terms of the series. Okay. And another interesting on the this is sign here, so let me cut and then let's write on this part. So this is sine, okay, sine. So we could say the sine, so we maybe start arrange sine within the Maclaurin, okay. So we could start by taking x equals 0, so 0. So we may be taking for several numbers. You will see that because it's always sine, cos, and every time we take 0 to sine, it will be 0, but every time we take 0 for cosine, it will be 1. And also alternating between 1 and -1. Then we can make some sort of short conclusion that we're going to have like an alternate series. So we could have f0 plus f prime 0 and every time it's even, it will be 0, right? So you will see that we have x, so this will be 0, 0, 0. So it will be x plus x squared over 2 factorial. Oh, sorry, 3. This is x cubed, sorry, x4. Okay. So x cubed 3 factorial plus this is minus, sorry, minus plus, okay, plus minus plus, okay, plus minus plus, so x5, and then minus plus okay, and we can express this, so this is sine x, so this will be equal to sum, and we can take the alternate series with -1 like that, and we have 2n plus 1 factorial, and then x 2n plus 1, odd number, right? And of course, if you are taking the Taylor's inequality, we can set, because the derivative of the sine is always sine or cosine plus minus, so it can be sine plus minus cosine, so we can set this expressions always less equal 1, okay, and we can also prove this with the same approach with the e to the x as previously mentioned, okay, by taking this sine x and then check the remainder, and it will be getting 0, and then we can prove that sine x is this this series, yeah. So we can also prove that. If we would like to see how it goes in the visuals, the graph, we see that this is 1, okay, and then 3, and then 5, and then it's always getting closer to the red curve sine x. Okay. Now, for cosine, since cosine is the first derivative, so basically we can take the series and then derive them as well. So we can take and this become just that. Okay. You could also try to set up the Maclaurin series as usual for cosine, and you will end up with the same conclusions. Okay. So I think that's the recap for what we have done on Friday. There are several other Maclaurin series that is important as well, but I think I will review that part in class. Okay.